Hello everyone, welcome to our Ask Geology group. So in this today's 7-minute numerical we are going to discuss about one very easy remote sensing question asked in Csir-Net, and this green banner that also represents our net questions. Okay, the question is very simple. What is the radiative flux? Okay, what is the radiative flux emitted from a black body at temperature 200 Kelvin? And given that the Stephen Boltzmann constant to be 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. Okay, so this is a Csir-Net question 2019 in June net. Okay, so now before just going to discuss this question, let us know about what actually a black body. Black body is a hypothetical body that absorbs everything. Okay, that is black body. Okay, so and whatever the radiative or radiative emittance, radiative flux that is being calculated by taking this black body as a parameter. So this is actually considered as to be a scale. Okay, so you can see, okay, the total emitted radiation from a black body is proportional to the fourth power of its absolute temperature. This is known as Stephen Boltzmann law, and it is expressed as m lambda is equal to lambda, and this is your sigma t to the power 4, and this sigma is called the Stephen Boltzmann constant having 5.6. This is the value it is given. So this is the simple formula you have to use to get the answer. Okay, and now you can see that the emissivity, like that type of parameter is being used. Okay, with reference to the black body. You can see that for any matter we can measure the emitting energy, and we can compare it with the emitted energy from a black body. Okay, so this black body is considered to be as the reference. Okay, considered to be as the reference. So the value and this emissivity value, the perfect reflector will have nothing to emit, therefore its psi, and this is epsilon value, will be 0. Okay, and a true black body has epsilon of value 1, but in nature that true black body is not present. Okay, true black body is not present, and everything, whatever all the other materials, they fall between in these two extremes, that is this epsilon value will be 0 to 1. Okay, so this Stephen Boltzmann law basically measures the total emitted radiation. Okay, total emitted radiation, or we can just call it as a radiative flux. Okay, radiative flux that will be emitted from a black body, and the temperature maintained is 200. So simply put the formula m lambda we have to calculate, and this value Stephen Boltzmann constant is given 5.67 into 10 to the power minus of 8. This is watt per meter square Kelvin to the power 4 into t to the power 4, t, that is 200 to the power 4, and Kelvin to the power 4. Kelvin will cancel out, then watt per meter square, that is the unit. So what will be the answer? This is 5.67 into 10 to the power minus of 8, okay, divided by multi into 200 to the power 4. This is actually 90.72. This is 90.72. This is watt per meter square. So this is nearly 90 watt per meter square. So here the D is our answer. Okay, so another interview related questions I just want to ask here, that why in many cases, okay, why we use this Kelvin scale, because to measure the temperature we have this degree centigrade scale, Kelvin scale, okay, and Fahrenheit scale. So many of other scales are present, but why we are using many a times that Kelvin scale? So what would be the answer? क्या होना चाहिए? Okay, so this Kelvin, 0 Kelvin, okay, this 0 Kelvin, that indicates the absolute zero temperature. Absolute zero temperature. What does this mean, absolute zero temperature? That means it is absolutely zero. The thermal energy, okay, the thermal condition, that becomes zero. Okay, there will be no such thermal energy will be present there. So the particle motion will cease. Okay, at absolute zero temperature, okay, particle motion that actually ceases. Okay, that becomes zero. And that's why we are using many times this Kelvin scale, because if we take that 0 degree centigrade, that is minus of 273 degree Kelvin, that means this 0 degree centigrade, there are some particle motion is still there. Okay, because it is not the absolute temperature. And for this very cause, we use many times the Kelvin scale. Okay, so this is all about this question. This is very simple, nothing to worry, but I just want to add something extra, that that is the radiation laws. There are three types of fundamental concept, or 3 types of fundamental radiation laws. Okay, the first is basically, the first theory treats the electromagnetic radiation as many discrete particles called photon or quanta, and the energy of a quanta is given by E is equal to h nu. E is equal to h nu. Okay, it is also called E is equal to h nu, or nu is equal to c by lambda. So hc by lambda, this is the first radiation law, in which the energy contained within a quantum is measured. E is equal to h nu. E energy of a quantum, that is joule. Okay, h is your Planck's constant. Okay, and nu is your frequency. So E is equal to hc by lambda. So energy of a quantum is inversely proportional to wavelength. You can see E is equal to hc by lambda. Lambda is your wavelength. Okay, this is your wavelength. C is your velocity of light in vacuum. H is your Planck's constant. E is the energy in joule. Okay, so another thing, this is actually a conclusion that has been drawn. If we want to sense emittance from objects at longer wavelength, we will have to either use very sensitive device or view a larger area to get sufficient amount of energy. And that's why this is related to your spatial resolution. How it is spatial resolution? If you want to, okay, so if you want to identify a particular object, okay, maybe this size object, then the wavelength you should use, that should be smaller, so that it can detect. Okay, if the object is this one and the energy you are using to detect is this much, then maybe it will miss this one. Okay, so for finer resolution, okay, so finer resolution, we will have to use the energy, or the energy which wavelength should be low. Okay, so this is, you can see, energy is equal to wavelength. If wavelength is more, then energy should be least. Okay, energy in this sense, in remote sensing case, what energy and this wavelength is just telling about these things. Okay, so wavelength means higher wavelength. If you are using a longer wavelength for the signal, okay, then the energy, that backscattered energy, the energy your sensor will get, the energy will be limited. Okay, the energy will be limited. That's it is actually trying to tell. Okay, and for depending upon that, the remote sensing in microwave remote sensor, you know, okay, for microwave remote sensor, how much of amount of energy we get back. Okay, in remote sensing, like in microwave remote sensing, this is active remote sensor, so you send some energy. Okay, this is wavelength, and this wavelength, we are talking about this wavelength, and after interacting with the particle which is present on the surface of earth, it just backscatter the amount of energy. Okay, so this value we are getting, okay, the value we are getting from the backscattered energy, this is actually our energy, or this is our signal we get. Okay, this is the signal we get. If the wavelength is more, then the signal will be less. That's actually the thing. Okay, and there is the second radiation theory, that is the Stefan Boltzmann law, that is related to the total emitted radiation and the temperature. Okay, it is the interrelationship between the total emitted radiation with the temperature, and that is the Stefan Boltzmann constant. It has a unit of watt per meter square per Kelvin to the power 4, and this is the amount of emissivity, and emissivity that is measured by, this is actually the emitting energy by the object to the emitted energy from a black body at that particular same temperature. Okay, that is the emissivity, and this is the second radiation theory or law. And third is the Wien's displacement law, that at what temperature, okay, at what temperature the maximum wavelength you can get. Okay, the third theory is the Wien's displacement law, which specifies the relationship between the peak wavelength of emittance and the temperature of a matter. Okay, peak wavelength कौन सा, like at which peak wavelength the temperature will be associated temperature with that. Okay, so in addition to the total amount of energy existing in a body, we can determine its dominant wavelength. Okay, lambda max, maximum wavelength, we can just calculate by using the Wien's displacement law, because depending upon the temperature, this lambda max that shifts, that gets displaced. That's why it is displacement law. And who just gave it? The Wien, that scientist. So this is Wien's displacement law. Okay, so K is a constant, that is equal to 2898 micrometer Kelvin, and T is the absolute temperature. Absolute temperature means that should be in Kelvin scale. That's why this is absolute temperature. If it will say absolute zero temperature, that means this is 0 Kelvin. Or absolute temperature, if I am just taking 100 Kelvin, this is in Kelvin scale, or it is absolute temperature. Okay, representation of absolute temperature in Kelvin scale. Okay, Sun approximates a 6000 Kelvin black body. Its dominant wavelength lambda max, you just calculate. Okay, no problem. In the next class maybe I'll just give. And this sun is considered to be as a black body. Okay, but a pure black body is not present in nature. Okay, so thank you. I hope this question is very easy, but I just tried to explain some related things which are connected to these numericals. Okay, so thank you. I hope I could help you in understanding these questions, and thank you. Save our Mother Earth, plant more trees, and thank you very much. If you are interested, then you can join our group by just simply calling to these numbers, or you can mail to this mail ID. There is a link tree given in the description box, so that if you just click, then that will direct you to all our social media platform available. So thank you, and keep practicing. All the best. Have a good day.